Hello. How are y'all doing today? I would appreciate if one of you could unmute and say a thing so I know that I can hear you.
Good. How are you?
Thumb up. Maybe even two thumbs up, but I'm gonna go with one for the moment. Just getting things set up so that way we can move forward. I like to have the chat window open because sometimes people chat something at me. And then also the participants window open simply because if one of you does unmute, I can often with the participants window quickly identify who it is much more easily than looking at the screen. So I think we're in a good place to start. I'm gonna, like normal, just share a frickin' screen and we'll just see what happens today. I think I've got that good. It looks as though everything's being recorded the right way. And let me just go and talk about a couple administrative things because I always do that. And then we'll get into the meat of it. Um, one is yeah, week two lab groups. So far, you've had three, no, two or three, two experiences with that. There's a lab group today that, I mean, lab today, like there was on Monday and like there was on Tuesday. And so you have the opportunity to sort of work with people again. And then just let me know, hopefully by, the fourth or fifth, um, the morning of the fifth, if you're going to wait until Sunday, if things are going well from your point of view in terms of lab groups. Hopefully they're solidified. Some people are really open to change, and that's cool. And some of people are thinking, well, as long as I'm not changing into a group with that person, because you had like a clash or something, just let me know. We'll work it out. One other thing I want to let you know is I didn't put this question on there, but if you email me a thought about this, it's not bad. Um, we could do a lab group of the whole if you're willing to work with a group of like six or seven people all at once. That's bigger than I think is optimal. But you're always welcome to chat with anyone in the course. Effectively, a lab group of the whole would be good from some points of view. On the other hand, sort of individual responsibility. And so if you think you'd rather it be exactly three people, cool, let me know. If you think the lab group of four or five, that's better for you, let me know. It will work out. So that's one thing I want to mention. Second thing is office hours in the morning already happened. A couple people showed up, not any of you in particular, but the afternoon office hours are normally later after the afternoon class, which goes 4 to 5. So it'd be like 5:10 to 5:35 on Thursdays. Not this Thursday. I have an appointment that I need to be at, and so to drive to get to there is right after the class. I'm going to shut things down. And so if you do have questions, come by between 3:25 and 3:50 today. Just click your way into the Zoom office hour link, which is like right around here. Um, and that should be good. Also want to sort of mention getting into the content of the week. Another reminder to fill out the lab group surveys. For those of you who have opinions, let me know those opinions. And yesterday we spent a little bit of time doing review content from the past. So I would probably, if I were not able to have been in class, or even if I wanted to sort of look back on yesterday, that's a video that you could watch for me yesterday. And then, like I said earlier, the July 6, 2023 exam review day was also really good. There's nothing wrong with the 2004 08 exam review. I'm just saying, though, it doesn't as cleanly match sort of where things are at as the 2023 July 3rd exam review. The homework problems today are all out of chapter 4 and the lab today again in chapter 4. We're diving into a new topic that I'll call sequential and adjusted sums of squares. It's in our book talking about multiple explanatory variables, chapter 4. That's the things that I wanted to make sure I said to you. Do any of you have administrative questions? How about subject matter questions in a general form? Don't ask specifically about like, oh yeah, what about this question on the test? Because, if you have started the test, great, wonderful, good on you. If you haven't, well, that would be unfair to have someone start asking a question about something specifically on the test. Do you have any general questions tied to content from the past, like even chapter 3? Okay. Cool, cool. Okay, so what I want to do then is to move forward into new material, and it's essentially chapter 4. Yeah, general linear models, like we said yesterday, no, yesterday, 2 class sessions ago, allow us to deal with many explanatory variables. And we learned in chapter 3 that the way we can cleanly do that with explanatory variables that are categorical is to say what is the effect of you being in this group on the response. So that's sort of what is the effect of being in the group on the response. Um, Grouping information, quantitative information, both could explain the response variable. Let's move forward and talk conceptually about the benefits of multiple explanatory variables. And maybe I should open up the dioecious trees data set. And we should have opened up the data set list before class started. Oh well. Aha, 313 and summer and all my data. And so let's go with the dioecious trees. Okay, come on. When the software opens for the first time, it takes a while. Okay, so here we've got the dioecious trees example data. We've seen it before. The DBH, that's the size of the tree. Number of flowers is the response. Size may predict the number of flowers. Let's verify that with a graph. Graph Builder says there might indeed be a relationship. Let's, darn it, got to move things around a little bit. Okay, here. There we go. Number of flowers. Can I predict it based on the size, diameter, breast height, DBH? And you're thinking, oh, look, we got a trend line drawn in. I might like it curved. I might like it straight. I'm just saying maybe I don't even need the trend line. I'm going to get rid of it. Question is this: how does sex, which is an M or an F, an A or a B, a 1 or a 2, a 0 or a 1, there's just different categories. That categorical variable in the little red looking thing says, oh, treat that like categorical. If I put this as a color, you can all spot, oh, look, reds, which is sex 2, are higher than blues, which is sex 1. Reds female, blues male. Sex 2 seems to have higher number of flowers than sex 1. If I put this as an overlay, it looks about the same. The benefit of overlay, though, is if I do turn on a trend line of sorts, it sort of shows me here is for each of these groups the separate XY relationship. Now, that's shown with a curve. There may be a better way to deal with these data, but I would say sex 1 has lower flowers than sex 2 at any given diameter at breast height. For example, 200 millimeters DBH. We've got a lower number, like about 100, and it's about 300 if it's a red. At any given DBH, any different X variable value, we see lower in the blue than in the red. We need a conceptual model that could handle that. And that's really where we're going in class today. Okay. Um, what are the benefits of doing this? Okay. Well, we're changing up our question a little bit. We're no longer saying, does the number of flowers depend on the sex, or does the number of flowers depend on the size of the tree as measured by DBH? We're saying, in one way, does the number of flowers depend on the sex of the tree, the size of the tree, or both? And if you have smaller errors, mean square prediction error, if those are down, we can predict more precisely. And we can even handle fun questions like, what is the effect of the size of the tree on the number of flowers, controlling for the gender of the tree, taking into account what sex tree it is, what is the impact of the size? Or flip that on its head, taking the size of the tree into account, what is the effect of sex? That's really what we sort of said. If you are saying it's a tree that's say 200 millimeters, what is the effect of blue versus red? Blue is a reduction of number of flowers by about 200 if it is a 200 centimeter or 200 millimeter tree. What if the tree's 250? The gap in the expected number of flowers, the predicted number of flowers, would be even larger. Okay, so we can tackle questions like, yeah, if we keep in mind the sex of the tree, I mean, if we keep in mind the size of the tree, what is the effect of the sex? One other fun thing about a lower mean square error, that is the denominator in an F test, in analysis of variance at the F ratio. And if the denominator is smaller, would the F ratio indeed be larger? Yes, it is. Larger F ratios have a smaller p-value. We're further out in that tail. Effectively, we can spot trends with these more complex models that we might not spot otherwise. I'm going to jump over the next last one and just say, oh, look, higher R squared, also good. Let's maybe move forward into an example and well, as we already talked about that one. Maybe we'll do it with JMP though. I showed you the picture. Let's go ahead and do this within JMP using analyze fit model. Okay. Analyze fit y by x. We said before, yeah, we could have the number of flowers depends on sex, one or two. Click OK. And we see, oh, look, there's a trend that the sex two have, it looks like more flowers than sex one. Is it significant? I don't know. Maybe we should turn that on. Let's do the t-test. Oh, we have a lack of significance. Our p-value is 0.222. I'd say I can't tell that there's a difference in the average number of flowers, but the picture frickin' shows there's a difference. We're saying comparing just the blues to the reds and the height on average, I'm not spotting a difference. The other sort of analysis that we could tackle is number of flowers depends on just DBH. Let's try that analysis. Analyze again, fit y by x. DBH, predicting the number of flowers. We're going to see, it looks like a trend, and some of you are like fussing at me under your breath reasonably. Is there a lack of equality spread? Very narrow range of y values, but a very wide range of y values. Yes, there is a lack of equality of spread. We should probably fix that. We'll see in a later chapter how to fix it. If I were to fit that trend line, I would say, oh, look, there is a relationship between DBH and the number of flowers. It looks as though there is a positive trend. Here we say we don't see a difference between the two sexes. Here we say we do see a trend across DBH. What if we want to tackle the question, flowers depends on sex or DBH or both? How do we pull that one off? Well, we can't use fit y by x anymore. We need to switch over into fit model, which we learned in chapter 3. That's the way we're going to go from here on out. I would simply say the number of flowers, what does it maybe depend on? I'm going to put in DBH because that was significant, and then sex second, that wasn't. And you don't have to put them in any particular order. We'll see in class later, there are some contexts where putting them in one order versus the other would be important. But for now, I'm just saying I'll toss them both in. DBH may predict number of flowers. Sex may predict the number of flowers. And we're now going to say, well, is there indeed a trend? I've looking at the output here. Okay, okay, there we go. Here is my new output, and I'm trying to highlight just the things that are key. With just sex, we could say there's not an apparent relationship. With DBH, we say there is a trend. Here we're now saying we're going to fit two trend lines, one for sex 2 and one for sex 1. And it does look as though the role of red versus blue swapped. Don't worry about that. I'm just saying, oh, look, we drew in two trend lines. And my F ratio for my model is like all of a sudden like 123. That's pretty big. Earlier it was only 114. My R squared went from 70 to 84%. Not bad. My mean square error was like 44, and now it's like 69. But I'm sorry, that's lack of fit. I apologize. My mean square error was 44. Now it's 24. It's lower. That's one of the reasons my F ratio is higher. And it seems as though we have an effect of sex 1 and a slope related to DBH. We're going to talk more about that in chapter 6. I don't want to sort of rush it now. I'm just going to say, oh, look, at least one of my x variables sort of matters. In analysis variance, we really tackle the question, is there anything going on here? It used to be, is there any difference across the groups? Now are any of my explanatory variables helpful? And the answer seems to be yes. And it looks as though I have a separate p-value for DBH. That's significant. And also for sex. We're going to have to, in chapter 4 and 6, come to terms with this. But overall, it's promising. Higher R squared, good. Higher F ratio, lower P value, good, good. It feels as though we're able to tackle this question. Controlling for DBH, is there a difference in the number of flowers between the males and the females? And also controlling for sex, is there a relationship between DBH and then the number of flowers? I can handle that. Any questions about the picture or the analyses thus far? Okay. So what I'm going to do then is move this out of the way and move forward. I'll smallify some of these because I don't think I'm going to come back to the data set here. Um, if we're trying to use the Pythagorean theorem to find the distance between the lower front left corner of a block and the right rear upper corner of a block, you're sort of saying, I think I could do that as long as the corners are right angles. And indeed, we have right angles if it's a regular little square block. Okay. So I've drawn those two in as right angles. And we know that the distance from M to S, if you will, the model that's just the mean to a model with sex of the tree. Okay. Well, I could say, you know what? There's a distance from no group difference to, I'm sorry. I apologize. I want to erase that term here. And I'm going to move this over here so I can work with it more easily. Good. Okay, so there's a model with no apparent x variables at all. That's just a model where only the mean is a constant. There's a number of flowers on the tree, and it does not depend on DBH, and it does not depend on sex. If we sort of go along this front right surface, the front right edge, to a model where DBH is in the model, okay, it seems as though that distance from M to D plus then the distance from D to S, the model with sex plus DBH, that A squared plus B squared is C squared. The distance from the mean to this point labeled S which really has, I would say, D plus S both in the model. Um, these distances, they square and sum. Okay, so I'm going to call this the sums of squares due to dBH. This second term, I'm going to say, is a sums of squares for sex given dBH is already in the model. And I guess if I have my partitioning of the sums of squares, this third term would be SS error, because indeed, if it's not attached to dBH, variability that we could explain, or variability associated with the sex after dBH has been added, what's left is error. Some of you are thinking, though, that's just going one of the two routes you could go along the front edge and then the right side. You could go along the left side over to a model with just sex in it, but not dBH, and then along the rear section. And because we have a right angle in that corner as well, from the mean model all the way to the model with both variables in it, there's two separate ways to add up those sums of squares. Literally, I could have this term here, sums of squares for the model with sex in it. And then I've got a sums of squares for dBH given you all have sex in the model. So it does seem as though we could get to the model with both terms by adding sex first and then dBH, or we could add dBH first and then sex. Which term should go into the model first versus second? That's really the question that we have here. Let's um, let's go down the path and consider both ways. I'm going to sort of I'm going to define this in a little bit. Let's give you the example first. And I'm going to sort of give you the example with, I guess, a GMP version of the data set. Here are data collected in 1972, and this is the life expectancy of people in a country in 1972, and the income that's in dollars per person per year in 1972. And this last column is corresponding to what type country is it, and there's two types. Industrialized countries like Japan or the Netherlands, or OPEC countries like Indonesia or Libya. So there's two types of countries, and the question is there a relationship between either income and life expectancy, or type of country and life expectancy, or maybe both explanatory variables have some relationship with life expectancy? So let's consider what these data are like. I'm going to first show you with Graph Builder that relationship. I guess income seems to be the explanatory. Life expectancy is sort of a response. And I don't like curves. I could make them straight, or I could even remove the trend line entirely. Do we see a positive relationship? You all say yes, thumbs up. What about if we include a type of country as well? And I'm going to include as country red versus blue. Do we see a difference, red versus blue? Yeah. And if I have it instead of as a type, but rather an overlay, I could now add in that trend thing, and I'm going to make them straight. Do we see in each group a trend line? Yes, we do. Let's go more slowly, though, and I'm going to do this with a picture that I hope is clear, meaning I hope you can see green and red and black. Here we've got along the x-axis income, on the y-axis life expectancy. And this green model is the mean model, where it basically says income does not impact your life expectancy. There's no slope. And also the green model ignores which group you're in, the red OPEC countries or the black triangle industrialized countries. We're just saying the average life expectancy, that's what we're betting on, is about like 65. Regardless of income, regardless of type of country, we're just betting 65 is the average life expectancy. Now let's consider a model, and the model on the right says, okay, we're going to use income to predict life expectancy, and that would be done with a slope. I'm going to draw in a trend line, the best fitting trend line, the least squares. I'm going to fit a regression. Now, we can see that these errors in green around the mean model are pretty big for all of these red X's over here off to the left. Big errors. Big errors are bad. The sum of the squared errors in total, SSY is what our book calls it, is pretty big. It's about 3,400. What is SS error now? Well, if I have these, can y'all see the cyan color?
I can see the cyan color.
I love that because sometimes if you can't see what I'm trying to show, that's sort of not good. Okay, so what we've got here is this cyan or light blue color trend line and the associated errors. It looks as though for these data points over here off to the left, the low income, low life expectancy countries, the errors are like mostly smaller. The sum of the squared errors is now not 3,400, but it's like that dashy thing downstairs. It's much smaller. And indeed, this sums of squares due to our regression model, okay, that is about 2,000 of the 3,400. In fact, our squared variable is just telling us what fraction of the total amount of variability of y could be considered explained by the x variable. Most of it. The error is what's left. I'm going to sort of show you how you could do that and get those numbers literally under analyze. And I'm going to go with fit model now because I can. Fit model, I'm going to say the life expectancy maybe depends on income. Boom. And that's it. I'm not going to put in the categorical variable. And I'm seeing overall in my ANOVA, my analysis of variance, and overall amount of variability, the 34, 33, that's this. What proportion or what, I guess, amount of variability, what is the sums of squares attached to our model? That's 1900. That's shown here in cyan solid. And then SS error, it's like what's left of what was the total variability, which is again shown here in green, dashy. Error is now much smaller because we have the trend line drawn in. So I'm able to explain a lot. Overall, that's just over half. Our square says 56%. Yay. So, yay, we know that there's a trend. It looks like there is a trend. We're happy about a trend. But there's two different groups. There's the red and then the black. It looks as though maybe we would do better if we also allow reds to be reds and blacks to be blacks and let there be a trend line in each group. We're going to create another model which includes both group as well as income information. And mouse down, click forward. This is off to the left, the model we had just fit. Cyan is sort of the intermediate model. We have indeed income first. And now we're fitting a model with a second variable for type of country. Upstairs is the blacks, downstairs is the reds. And those associated errors, they're all really tiny in the upstairs group. They're sometimes pretty big in the OPEC downstairs group, but the sum of the squared errors, the dashy lines away from the trend, very small errors, yeah? Let's show you how you would get that analysis done. Okay, so analyze, fit model like before. And in this lab coming up, the recall button is really helpful, so I'm going to start to use it. I'm just going to say, just show me what I just done. Oh, in addition to income, I want to put type of country in there as well. Rerun the model, this new model, and we can see, yeah, we drew in two trend lines, not the same colors as before, unfortunately, but we do have the two trend lines. And R squared is now higher, 85%. My analysis of variance is overall across the model what's going on. But it does look as though the errors now are only 530. In the model, the pink model overall explaining 2902 of the 3433. Pink 2902 of the 3433. And the error is about that 500 difference there. What we're spotting is the errors are now a lot smaller than they were before. The errors here were like, geez, 1,500. Now they're only 500. We're explaining things better. How much better are we explaining things? The amount better that we are off is this dashed, and I should have made it solid. I'm sorry I didn't make it solid, but it's this dashed blue line. Dash dark blue. Cyan is like, what do you get? What's the benefit of putting in income? And then the dashed blue line here is, now how much better off are we? Because we're adding in country type. We're reducing the errors from big to really pretty small. So it seems as though we're able to do pretty well with both explanatory variables. Overall, R squared was like 85%, much better than before with only 50%. I'm much happier with this second model where we have both explanatory variables in it. But one of you is always going to ask if this is a bigger class. But you're probably thinking anyway, why income first and why type of country second? Couldn't we have put them in the other order? And the answer is, yeah, we could have. So let's go ahead and do that. So again, maybe comparing to our original model, the green one with one mean, if we're comparing to the green model, just two groups alone are blacks versus reds, are industrialized versus OPEC countries. How well do we do? We're able to explain really quite well what's going on. Let me show you the model and how we could get that. Under Analyze Fit model, again, I think recall is really helpful. I'm going to recall, boom. And I'm going to remove income, being left with just type of country. I hit run. Shoot, I hit run and then move it over here. And let's zoom in on the things that we really want. R squared's like about as high as before. The model with both terms in it, the pink model, seems to be fitting about as well as our dark blue model, which has just country type alone and is ignoring income entirely. R squared's about as high. My sum of squares for the model is about as high. My sum of squares error is about the same as if we had both. If we effectively put in country type first and then income, country type is explaining an awful lot, and income doesn't do hardly much for me at all. It's very dissatisfying to look at income the first way we went. Well, let's put in income first, and it does a great job. And then we put in country type, and it's like, great, good, and then good. Here we're putting in country type first, and then we're saying, and then income doesn't really help much. The question comes maybe, what model should we use across the three? Clearly, income alone is not as good as income and country type. Is income and country type better than just country type alone? I think it's about as good. So should I go with the model with both variables or just country type? Just one. The purpose of today's class isn't to actually tackle that question. The purpose of today's class is to literally say, let's talk about the order that you could put the variables in the model. Our sequential sums of squares approach is the following. Put in one variable, the variable you'll call the first variable. Find sums of squares for the model. Sums of squares for the model is what you write down. That is the first sequential sums of squares. And then you add in the second variable, and you're going to then say, how much better is SS model now? The difference in SS model with one variable to the SS model with both variables, that is the sequential sums of squares for the second term. It's how much better off are we? You could also say the exact same thing in terms of, well, how much is SS for the model? And then you go on and say, how much lower is SS error by adding the second variable? It will give you the same number. So we could line them up in any particular order of interest to us. And then we are tackling the question, do we want this variable? The first one. Yes, cool. Then now that we have the first one in the model already, do we want the second one? We're giving you a conditional test. Does X2 matter now once you already have X1 in your model? Okay. Um, so that's the way to go. That's the definition of sequential sums of squares. And the lab walks you through that slowly and carefully. I'm going to say though, JMP gives you the opportunity to get sequential sums of squares for free. Let me show you how you could get that. If I've got a model with both in it, maybe I should create that model. Again, analyze, fit model. And if I recall that, and I would say I already had country type, let's put in life expectancy no, that's my Y. Let's put in income second and say, well, country type first and then income second. If I run that, JMP tells me all the stuff that I want. This part down here where it says these effects tests, that is not the sequential sums of squares. To get sequential sums of squares, it's one of those things where you have to say, we have a default set of options. Under estimates, what do I want? Well, I want the sequential tests. My sequential sums of squares is found under, again, you do your analysis under estimates, then turn on those sequential tests. And yeah, literally the first test is it better to have country type than no variable at all? The answer is yes, it is. And if you already have country type, is income helping you? And we're saying we don't see a benefit of income. We could have put them in the other order. Let's go ahead and try that. Recall. I'm sorry, that's not fit. I wanted fit model. There we go. I'm going to hit recall now. What if we put income in first and then type second? Again, you're going to get that same thing that we just looked at. I mean, it really doesn't matter which one you put in first. It's going to give you the same overall fitted line. But if we're looking down here at our, I guess, our effects tests, it looks like just before. But again, we said we need the sequential sums of squares. So under estimates, sequential tests, how would I interpret this? I would say, is income better than nothing at all? Yes, it is. And if you have a model with income in it already, is adding in country type helpful to me? Yes, it is. So our choices are putting in type first and then income, and you'd say type matters. Or you could put it income first and say it matters, and then type afterwards and say, yeah, given income's already in the model, do you need type as well? Yes, you do. Is one of these better than the other? Do you need both variables like this would suggest, or do you need only one variable like the first analysis would suggest? Essentially, the software output, what we see in the effects test, and think of that as what our book calls the adjusted sums of squares. The adjusted sums of squares for a variable is the sequential sums of squares for that variable if that one had been last. Let me rephrase that. Controlling for or allowing all the other x variables to explain variability in y. Allowing every other x variable to explain something that's going on. Do we still see evidence that this variable is helpful? The adjusted sums of squares for a test is basically sequential, but last, and it tackles the question, hey, if you already had everything else, does this one still prove itself? Let's verify that in the context of our two analyses. If we'd put in type first, we say, yeah, that one matters. And then if you put in income afterwards, income being second, the sequential sums of squares here has a 0.17 F ratio, a p-value of 0.2018. That's the sums of squares in the effects test, the adjusted sums of squares for income is like sequential but last. If we had, however, chosen the other ordering and gone with sequential income first and then type sequential but last, that's where you see the adjusted sums of squares for type. Literally, my sequential sums of squares for type, that 959, we see that up here, 959. If you already had income in the model, would type be helpful? It seems with an F ratio of 45 and a p-value of tiny, yes, it is. So these effects tests are controlling for the other X. Does this X help us? Yes and no. That should cleanly allow us to answer the question, which is the model we would want to use across the three options. I'm thinking if I tell you with type in the model, you don't really need income. But if you had income in the model, you certainly need type. It says type should be included, whether income is included or not. And if type is in the model already, you don't need income. Just have country type alone as your explanatory variable. Any questions about sequential or adjusted sums of squares? And I know there should be a lot, but often in this class, it takes working through the lab to grapple with sequential and adjusted. This is also why I wanted to have the first exam before this topic. That would be pretty rude, I think, to sort of like have a lecture on something, and then all of a sudden the next day there's a test. It takes a little while to grab onto the material in chapter 4. Okay, so I want to close with our book has these two brilliant examples that we're going to call poets and legs. And adding a second explanatory variable can often be super helpful. So let's try it with a poets data set. Here are data on a collection of famous poets' age at death and their birth year. You might want to know, hey, do people live longer nowadays than people used to live hundreds of years ago? Silly question. The answer is probably yes. How would we check that? Well, we don't know the age of everybody who lives these days when they die. We don't know their ages, and even less do we know the ages of people in the year 1200 when they died. Okay, not a lot of information on a lot of the regular people. Uh, we do have information about famous poets, however, who are not always from the upper class. Upper class individuals tended to live longer just because they were upper class individuals. Poets came from a more widely varied collection of classes and are also more likely to have been recorded their birth year and death year than famous merchants. So let's get the poets. Birth year, poets, age of death. That should produce a plot that helps me understand whether there's a relationship. And let's try it. I'm going to go with fit y by x for now because we're in the context of we're going to do a model. And fit y by x will draw me a nice line. Poet's age of death, poet's birth year. Boom. Is there a trend? Well, let's look. I'm going to add that trend line in, and it says my F ratio is like 0.0035. My P value is 0.9541. I don't see a trend. You don't see a trend. And R squared of about 0.000, there's no trend. I would say I don't see evidence that a birth year would allow me to predict the poet's age at death. Let's change our question up a little bit, though. And you're going to sort of start to laugh if you haven't already. Can I predict the age of a poet at death with either the poet's birth year or their death year or both? And this is where in a regular classroom Someone's always giggling in the back, in some sort of academic way, because giggle sounds silly. They're laughing because, duh, you can. You subtract the birth year from the death year to get the age at death, give or take a half a year. We're going to know it exactly. And my model that I fit, where I include both X's, I'm able to explain 99.9% of the variability as opposed to just birth year alone. None of the variability is explained. My F ratio is like highly significant. Have never seen an F ratio like 5,000 before this data set. And you're going to say the slopes in a regression are like death year times one minus birth year times one. What about these effects tests? This effects test for birth year says if we already had death year in the analysis, does adding birth year in help us? Yes, it does. If death year were already in the model, does adding in birth year help us? Yeah, I'm sorry. If birth year were already in the analysis, does adding in death year help us? Yes, it does. If we had turned on under estimates sequential, you would say, is birth year helpful? I don't see it. Is death year helpful above and beyond what you have if you have birth year? Certainly it is. It seems as though both variables are in the situation of, I'm not really helpful by myself, but I'm definitely helpful if I'm in the context of the other X variable. We have if birth year were first, is it helpful? I don't see it. Death year, if birth year were already there, heck yeah. Let me go ahead and try that again in the other order. I'm going to use recall and put birth year in that second slot. And I'm going to sort of zip down to where I have my, nope, not all of that. Zip down to where I have just my sequential sub. Oh, actually, no, my effects test is the same as before. Because again, effects test, it doesn't matter which order you put them in. But if I had now under under estimates sequential, if I'd done them in the other order, is death year. Hold on a second. Is death year helpful? It seems to be. It seems to be helpful. Is birth year helpful given that death year is helpful? Yes. Okay. So it seems as though I would say here birth year by itself, nah. Death year by itself, yes. But I'm going to basically say, are both of them super helpful in conjunction with the other one? Yes. I want to pursue this a little bit more. This sequential sums of squares, death year being first. If I had death year, and this is what I probably wanted to do instead, if I had Pote's age at death as a function of just year of death, the graph looks about the same as before. And if I'd fit in a trend line, yeah, if I'd fit in a trend line, we wouldn't have seen much of a relationship. Okay. It's only in context of the other X variable being there also that the current X variable is deemed helpful. Okay. Last thing I want to mention is our data set on the legs, and it's like the poets, except for it tells the exact opposite story. Yeah, literally, if I have a person's left leg length and their right leg length, could I predict their weight? My bet is just one leg would maybe allow me to predict the other leg's length. I'm going to do the analyze fit y by x pretty quickly. Weight depends on left leg length. Click OK. I see that's pretty trendy. That was a joke. As see a trend, so it's trendy. I'm able to explain 56% of the variability overall. There's a definite statistical significance. My I do want to turn on the effects tests. Okay. And so that is up here. No, shoot. That is in the other method. Darn it. I wanted to have used fit model. I apologize. Fit model weight is predicted by left leg length. So it's the same thing as before. It's just that we get the trend line drawn in for free. And I have my R squared here. I'm going to leave that and my model ANOVA. And I'm going to ignore parameter estimates, but I'm going to show you the effects test. And the effects test says, yes, you definitely benefit from having left leg length in the model. If I were to do the analysis with both terms, however, fit model, I'm going to recall. If I add in right leg length as well, click OK. Again, removing the things I don't need and showing you only the part that I want to use for drawing a contrast. R squared is about the same. Knowing a person's right leg length as well as their left leg length doesn't really help me predict their weight. But under effects tests, I see something that looks really different. Left leg length alone before said, yeah, I matter. Left leg length here says, I don't really need the left leg length if I already had right leg length in my model. Let's rephrase that. It's superfluous information. These two X's are so highly correlated with each other. You don't need them both. Let's just show you with Graph Builder and then call it a day. If I tell you a person's right leg length, do you approximately know their left leg length as well? The answer is yeah, people tend to have two legs that are about the same in length. The information in the second variable doesn't add any benefit to us. So our effects test, our adjusted sums of squares says you don't really need either of them. Actually, no, it doesn't. It says if you already had the one, you don't need the second. At least one of the two variables matters. And if you have the one, right leg length, you don't need left. Or if you had left leg length, you don't need the right. Which one should you use? Does it matter? I don't know. We'll talk about that in a later chapter. Okay, we're at a good place to stop. I want you to enjoy the rest of your day. I'm going to, unless you tell me not to, I'm going to stop the share. And again, unless you tell me not to, I'm going to stop the recording.